In this video, we're going to learn another technique of integration called integration with partial fractions. Now, the calculus in this section is not too terrible. What's going to get you is the algebra. So I hope you're ready to long divide polynomials, factor a bunch of polynomials, and do a lot of systems of equations and fun things like that. So you're going to need very strong algebra to get these problems set up. Let's get started. So partial fractions are used when you're trying to integrate a rational function. That's a polynomial over a polynomial. And the goal is to kind of rewrite it into easier functions. I just want you to observe before we even start calculus. If I take two very simple little rational functions, 2 over x minus 1 minus 1 over x plus 2, we could write it together as one rational function by getting a common denominator. We'd have 2 times x plus 2 minus 1 times x minus 1 over x plus 2 times an x minus 1, which we could then simplify, distribute on the top, combine like terms. You'll end up with x plus 5 over x squared plus x minus 2. Now, the goal that we're going to have in this section is we're going to be integrating functions that look more like the ending here and doing this procedure backwards to write it as easier functions to integrate. So without even showing you how we do it backwards yet, the whole point of this is so that perhaps we have to integrate this function I just found here, x plus 5 over x squared plus x minus 2 dx. Well, going backwards in the work I just erased, we would have this is equal to integral of 2 over x minus 1 minus 1 over x plus 2 dx. And then both of these I can integrate using natural logarithms. I'd get 2 natural log absolute value of x minus 1 minus a natural log absolute value of x plus 2 plus a c. And it was much easier to integrate when it's written in that form rather than written with the common denominator. So this is the technique of writing as partial fractions. However, the question is, how do we get from here to there? And that's what we're going to learn how to do first. So just in general, we first have to consider a rational function, just any rational function. So consider a rational function, f of x equals p of x over q of x, where p and q are polynomials. Then we can write f as a sum of simpler functions if the degree of the polynomial on the top is less than the degree of the polynomial on the bottom. If it's not, well, then you're going to have to long divide first. Hopefully you remember polynomial long division from pre-calculus. I will put a link in the description below with a link to a video on how to long divide polynomials in case you need it. So let's just go ahead and do an example where we're going to rewrite our function just using long division first, and then we'll build up to the whole partial fraction process. So example, let's find the integral of x to the third plus x over x minus 1 dx. First, notice the degree of the numerator is 3, degree of the denominator is 1. So I have to start with long division, otherwise I can't rewrite it in a way that makes it easy to integrate. So I'm going to do this particular long division all the way through, but all of the other long division in this video, I'm going to skip showing all of the work just to save us some time. So make sure you watch that long division video if you need it. So long dividing these polynomials. I have x to the third plus x divided by x minus 1. I would get x squared, and then subtract what I get when I distribute, and I get x squared plus x left. That means I need to now multiply by an x, distribute that, subtract what I get, and I have a 2x, and that means I need to multiply by a 2. Ran out of room there, but let me just put it over here. We had a 2x. When I distribute my 2, I get a 2x, a minus 2. Subtract that line, and I get 2 as my remainder. So this means that I get x squared plus x plus 2 plus my remainder over the thing I was dividing by. There's the answer for the long division. So now I can rewrite my problem after long division. So after we do our long division, we should have an integral of x squared plus x plus 2 plus our remainder, which was 2, over the thing we were dividing by. And now this is already set up and ready to integrate without doing any other simplifications. It's just a power rule, constant rule, natural log, and we're done. So I get a 1/3 x to the third, a 1/2 x squared, a 2x, and a 2 natural log absolute value of x minus 1 with a plus c. Notice that technically to do that last integral, I did a u substitution, u equals x minus 1, but then du would just be dx, so I didn't have to multiply or divide by any sorts of numbers. It just ended up being natural log absolute value of u, and plug that back in. So I just did it without writing it all the way out. Now, this is how you would do it using long division. But what if we don't have long division to do in the problem? What if the numerator already has a smaller degree than the denominator? So if there's no long division necessary, or it's not enough to finish the problem up, now we have to factor the denominator. So if no long division, or if it's not enough, completely factor the denominator. And then we get to rewrite that rational function using partial fractions. And we have a bunch of different cases. I'm going to outline case 1 right now, and we'll do an example of that all the way through case 4. Though there's really more than 4 cases, but you'll get the idea from just the 4. So case 1. The denominator is a product of distinct linear factors. So that means the denominator, which we were calling q, looks like a1x plus b1 times a2x plus b2 all the way through anx plus bn. All just linear factors, and all of the factors are different. Well, then there exist numbers A1, A2, all the way through AN, such that our rational function P over Q looks like A1 over the first factor plus A2 over the second factor, all the way through your last constant over the last factor. Now, the hard part is finding those constants, the capital A1 through AN. You can find those by just using algebra. And the best way to learn how to do that is to just see examples. So let's go ahead and do an example where we end up with a product of distinct linear factors for our denominator, and we'll find the partial fraction expansion of this rational function. So let's do the integral of x squared plus 2x minus 1 all over 2x to the third plus 3x squared minus 2x dx. Now take a look. My denominator has a higher degree than my numerator does. So that means I don't have to do any long division this time. That means we get to start by factoring the denominator completely. So factoring the denominator. I notice that there's an x in common, so I can pull out an x, leaving 2x squared plus 3x minus 2. And then I can keep factoring this, and I get a 2x minus 1 and an x plus 2. So my denominator completely factored is x times 2x minus 1 times x plus 2. That's 3 different factors. They're all distinct. Notice they're all linear. They don't have any exponents on them. Well, other than an exponent of 1. So we have a product of 3 distinct linear factors. So this tells me that my original rational function, x squared plus 2x minus 1, over this guy factored, that's my original function. This is equal to some constant over the first factor plus some constant over the second factor plus some constant over the third factor. And now we just have to figure out what those constants are. And now this is where the algebra comes in. To figure out what those constants are, the first step is multiply both sides by this factored denominator. So on the left side, the denominator will just cancel out completely. And on the right side, each of these 3 terms gets multiplied by that entire factored denominator. And it's going to cancel out all of these denominators, but it's going to leave things multiplied on the A, the B, and the C. So let's go ahead and do that. Multiply both sides by the factored denominator, and you get x squared plus 2x minus 1 equals the A. When A is multiplied by this denominator, the x cancels out, but I still have 2x minus 1 and x plus 2. And then my B, the 2x minus 1 cancels out, but I still have x and x plus 2. And then for my C, the x plus 2 cancels out, but I still have the x and the 2x minus 1. Now, how do I find A, B, and C from there? Well, there's a couple options. On this first problem, I'm going to do it by just distributing everything and combining like terms. So when I do that, I have x squared plus 2x minus 1 equals, distribute all of that, I will have a 2a x squared plus 3ax minus 2a plus bx squared plus 2bx plus 2cx squared minus cx. So that's just distributing everything out. And now I'm going to group things together. I have x squared plus 2x minus 1 equals all of my x squared terms. I have 2a plus b plus 2c times x squared. Now I look at all my x terms and I get 3a plus 2b minus c times x. I guess let me write that on the line below because I don't have room. So that was 3a plus 2b minus c times x. And now just my constants, which all I have is a minus 2a as my constant. So this is what we have down here right now. 1x squared on this side has to equal 2a plus b plus 2c x squareds on the other side. We're just going to compare our coefficients. So comparing our coefficients, we can set up a system of equations. For x squared, the coefficient on the left side is 1. On the right side, it's 2a plus b plus 2c. Now looking at my coefficient of x, I have 2 for the left side and 3a plus 2b minus c for the right side. And then looking at my constants, -1 has to equal -2a. If I solve this system of equations, I'll have my constants a, b, and c. Now luckily, the bottom equation here, we can solve that right away to get one of our constants. A is equal to 1/2. So since A is equal to 1/2, let's go ahead and plug that into the other two equations. I get 1 equals 2 times 1/2, which is 1, plus B plus 2C. And 2 equals 3 times 1/2, that's 3/2, plus 2b minus c. If I move the constants to the other side, these two equations become 0 equals b plus 2c, and 1/2 equals 2b minus c. So I have these two equations left to solve, and I'm going to solve it using elimination. I'm going to multiply my bottom equation by 2, and then add my two equations together. So my top equation is 0 equals b plus 2c. My bottom equation, when I multiply by 2, is 1 equals 4b minus 2c. Add the equations together to get 1 equals 5b, and so b is 1/5. And now that I know what b is, I can figure out what c is. So using, I guess I'll do the 0 equals b plus 2c, I can figure out my c. 0 equals b plus 2c means that my c is going to be equal to a -1/10. So we had a was, I already forgot because I erased it. My a was equal to 1/2, b is 1/5, and c is -1/10. So now we can rewrite our rational function using its partial fractions, and then we can finally integrate it. So remember what our rational function looked like. We had x squared plus 2x minus 1 over the 2x to the third plus 3x squared minus 2x. And we said this was going to be a over x plus b over my 2x minus 1 plus c over x plus 2. And we just found a, b, and c. A was 1/2, so I could write this as 1 over 2x. My b was 1/5, 1 over 5 times 2x minus 1. And my c was a -1/10, so that's 1 over 10 times x plus 2. And this means that my integral can now be written using this expansion. And I'm going to write it slightly different so it's easier to integrate. 1 over 2x, that's 1/2 times 1 over x. Plus, I have a 1/5 times 1 over 2x minus 1. And then minus a 1/10 times 1 over x plus 2. All with respect to x. And now we can integrate. All of these constants get to stay there, and we just have to find the antiderivative. The antiderivative of the 1 over x is natural log absolute value of x. So I get 1/2 times natural log absolute value of x. Now on this guy, you do have to do a u substitution. U equals 2x minus 1. When you do that, you're going to get du equals 2 dx. So dx is du over 2. We're going to have to be multiplying by 1/2. So when you do that substitution, this 1/5 gets multiplied by that 1/2. So you get 1/10 natural log absolute value of 2x minus 1. Now this last guy, technically there's a u substitution, but du is just dx, so you don't have to worry about any extra multiplying or dividing. I get minus 1/10 natural log absolute value of x plus 2, and then don't forget your plus c at the very end. And there we go, we did it. We just finished case 1 of partial fractions. That is probably the best scenario because it's just distinct linear factors. But now what happens if the linear factors aren't distinct? Well, that gives us case 2. Case 2. The denominator, q of x, is a product of linear factors, but some of them might be repeated. So for a factor, a1x plus b1 to the rth power, so that means that my linear factor a1x plus b1 is repeated r times. Then we're going to have r different terms corresponding to this denominator. We would have the terms a1 over a1x plus b1, a2 over a1x plus b1 squared, a3 over a1x plus b1 to the third, all the way through ar over a1x plus b1 to the r power. So you have to write each different power of that factor in the denominator, and you have a term for each power. So if you had a factor that had just the third power, you would have 3 terms for it. One would have the denominator with no power, then a second power, then a third power. So as an example, because I know this abstract way of writing it kind of makes it a little confusing. So for example, if I had x to the third minus x plus 1 over x squared times x minus 1 to the third, we have 2 linear factors. The first linear factor is x, and it's repeated twice. My second linear factor is x minus 1. It's repeated 3 times. So for the linear factor of x, I'm going to have a over x and b over x squared, 1 term for each power of that linear factor. Now for the other linear factor, again, I get 1 term for each power of it. So c over x minus 1 plus d over x minus 1 squared. and e over x minus 1 to the third. And that's how you would set up the problem. And then you would have to find your constants a, b, c, d, and e by multiplying by the factor denominator and using algebra, like the last example. So let's go ahead and do an example of this case all the way through. So first, let's find the integral of x to the fourth minus 2x squared plus 4x plus 1 over x to the third minus x squared minus x plus 1 dx. And the first thing you should do is examine the degree of the numerator and denominator to determine if you need to long divide. Now, the degree of my numerator is bigger, so that means, yes, we would have to long divide this first. I'm going to skip the long division work and just tell us that after we long divide, we'll get an integral of x plus 1 plus 4x over x to the third minus x squared minus x plus 1. So unlike the first problem that had long division, we're not finished yet. I can do the antiderivative of the x and the plus 1, no problem. But for this guy, we need to factor the denominator and find the partial fraction expansion. So let's just find the very, very last term for this integral. So doing partial fractions on this last term. First, let's go ahead and factor this denominator. I can factor by grouping. So if I pull out x squared, we get x minus 1. And then I can pull out a minus 1 and get an x minus 1. And this tells me I have 4x over an x minus 1 times an x squared minus 1. And that factors even further, because x squared minus 1 is a difference of squares. So fully factored, I get an x minus 1, an x plus 1, and an x minus 1, which we can write as 4x over our x minus 1 squared times x plus 1. So now notice my denominator is a product of linear factors, but they're not distinct. My first linear factor, x minus 1, is repeated twice, and then my other linear factor just happens once. This means I'm going to have 3 terms in the partial fraction expansion. So let's set it up. We have 4x over x minus 1 squared times x plus 1. I know I'm going to have one term for each power of the linear factors. So I have a over my first linear factor plus b over that first linear factor squared plus c over my last linear factor. And now I just need to find a, b, and c. To find a, b, and c, multiply both sides by the factor denominator. That will get you 4x equals a times an x minus 1 and an x plus 1 plus b times just x plus 1 and a c times an x minus 1 squared, because everything else has canceled out. And now from here, what we could do is we could distribute everything like we did in the last example and compare coefficients, setting up a system of equations. But there is actually an easier way to do some of these. So this is an equation, which means it's going to be true. So I'm going to pick some values for x that are easy to work with. For example, if I plug in x equals 1 into this equation, my left side will be 4. My right side, when I plug in x equals 1, this a term disappears because the 1 minus 1 is 0. My c term also disappears, so I'll just have a b times a 1 plus 1, and that tells me that b is going to be equal to 2. And is there another easy term that I can plug in? Well, I can plug in x equals -1. When I plug in x equals -1, the a term goes away and the b term goes away, and I just have the c term, which is c times -1 minus 1 squared. Well, -1 minus 1 is -2. Square it to get 4. -4 equals c times 4 means c is -1. So now I've already found 2 of my constants without having to do all of the distribution. Well, let's go ahead and see if we can just pick another easy to work with value and find a. There's unfortunately nothing that's going to make the b and the c both disappear without making the a disappear. But let's just see what happens if I plug in x equals 0, because that's easy to work with. If x is 0, my left side is 0. My right side will be a times a -1 and a +1, plus a b times 1, and plus a c times -1 squared, which would just be a 1. So this tells me 0 equals a -a plus my b, which was 2, and plus my c, which is -1. And this tells me that my a is going to be equal to 1 when I just solve this for a. So now I have a, b, and c. You would have gotten those same results by doing all the distribution and comparing of coefficients. It's good to know both methods because this method is usually a little quicker, but sometimes you need to use the other one because this method won't get you everything that you need. So let's go ahead and rewrite what we have. I know a is 1, b is 2, c is -1. So what was my original integral looking like? Well, my original integral, we had already written it, so it looked like x plus 1 plus 4x over the x cubed minus x squared minus x plus 1 dx. And all that work we just did finding a, b, and c was to rewrite this last term. So using my a, b, and c that we found, I have my x plus 1 plus my a over x minus 1 plus my b over x minus 1 squared plus my c over my x plus 1 dx. And now we are ready to integrate. This guy's a power rule, that's a constant rule, that's a natural log. The last one's a natural log. Be careful with the one in the middle. This one's not a natural log. You can rewrite it as an x minus 1 to the -2 power. Do a little u sub if you need to. Doing my antiderivatives here, I'm going to get a 1/2 x squared plus an x, a natural log absolute value of x minus 1. This guy will get me a -2 over x minus 1. And then my last one's a negative natural log absolute value of x plus 1 plus our c. If you need to see what happened on this term right here, where I got -2 over x minus 1, just know that I rewrote this one term as 2 times x minus 1 to the -2 power. I did a u substitution with u equals x minus 1. Du would be dx. And you just do a power rule with that guy. Plug the stuff back in and you should get right there. All right, so that was case 2, when you have linear factors, but sometimes some are repeated. Now, what happens if we have factors that are not linear? Well, then we get to do something a little bit different, but it's not too terrible still. So this is going to be case 3. your denominator has irreducible quadratic factors. With no repeats. What that means is if we have a factor that looks like ax squared plus bx plus c, it's a quadratic, but it doesn't factor into linear factors. Well, then the partial fractions has a term that looks like this. Instead of just a constant on top, we'll have a linear term on top, ax plus b over my quadratic factor. So, for example, let me write down an example for us so you can understand what I'm saying about how to write the form. So, for x over x minus 1, x squared plus 1, and x squared plus 4, my first factor is linear. My other two factors are quadratic because of that x squared, but they can't be factored any further without using complex numbers. So this means the partial fraction expansion of this, the linear guy, you still do the same way, a over x minus 1. But for the quadratics, I'm going to have a bx plus c over the first quadratic factor, and a dx plus e over the second quadratic factor. And then you just have to find your a, b, c, d, and e using algebra again. And again, it's multiply both sides by the factor denominator, maybe distribute into a system of equations, or plug in different values to find your constants. Now, before I do an example all the way through of this, here's a little reminder for you. You should know this from Calc 1, but I know sometimes people forget. If you have an integral that looks like 1 over an x squared plus a squared, that is equal to 1 over a times the inverse tangent of x over a. And some of you probably are used to seeing inverse tangent as arctan. Same thing, use whatever notation you like better. These come up quite a bit when you have irreducible quadratic factors. So I just wanted to remind you of that before we get to an example. All right, so an example of case 3 all the way through. Let's evaluate the integral of 2x squared minus x plus 4 divided by x to the third plus 4x. Okay, first note, we do not need long division on this one because the degree of the numerator is already smaller than the degree of the denominator. So luckily, no long division this time. That means we get to go ahead and factor the denominator and find the partial fraction expansion. So factoring the denominator of this rational function, I can pull out an x, and that leaves x squared plus 4. Now, I can't factor it any further because the x squared plus 4 is irreducible unless I'm factoring over complex numbers, but we're using real numbers in calculus, so we don't need to worry about that. So this means my denominator is a product of a linear factor and an irreducible quadratic factor. For the linear factor, I'm going to have a term that looks like a constant over my linear factor. And then my quadratic factor is going to have a bx plus c over my quadratic factor. And now we just need to find a, b, and c. To do that, multiply both sides by the factor denominator. So I get 2x squared minus x plus 4 equals a times x squared plus 4 plus my bx plus c times x. And now we just have to find the a, the b, and the c. I'm going to use the technique from the last example. If I plug in x equals 0, that will get rid of the bx plus c term, and I can find a pretty easily. So let's plug in x equals 0 and see what we get. If I plug in x equals 0, the left side of the equation becomes 0 minus 0 plus 4, so just 4. And the right side, I get a times 0 squared plus 4. And the rest of that is 0. So I get 4 equals a times 4. This means a is 1. But take a look over at this. There's nothing that I can plug in for x that will make this a term disappear and make it easier to find b and c. But what I can do is plug in a equals 1, since we know that's true. So if a is 1, I just have x squared plus 4 plus my bx plus c times x. I'm going to go ahead and distribute that. So bx squared plus cx. And now let's just play with this a little bit. I'm going to go ahead and move this x squared and the plus 4 over to the left side. That gets me x squared minus x, 4's go away, equals bx squared plus cx. Now compare what coefficients we have left. This tells me 1x squared has to equal bx squared. So that means b has to be 1. And negative x has to equal cx, so c has to be negative 1. So I have a is 1, b is 1, c is negative 1. Now we're ready to go back to the integral, write it with partial fractions using these constants, and it should make our integral much easier to calculate. So here was my original integral again. I had 2x squared minus x plus 4. The denominator, we had factored it to be x times x squared plus 4. I'm going to rewrite this with the partial fractions. It was my a over x plus my bx plus c. So 1x minus 1 over my x squared plus 4. Now I know it looks a little silly having a 1x there. I'm going to go ahead and erase that one. I was just emphasizing that it was my bx plus c. It's just my b happens to be 1. Now how do we integrate this? Well, I personally would take this last term and split it into 2 fractions. So I'm going to have my 1 over x. Then I'm going to have an x over x squared plus 4. And then I'm going to have a minus 1 over x squared plus 4. So now take a look at what we have. The first guy is a natural log. The last guy is your inverse tangent that we just reminded ourselves of. And the guy in the middle, you need to do u substitution. That one's probably the trickiest one. The guy in the middle, you're going to do u equals x squared plus 4. So du will be 2x dx. Du over 2x will be dx. That means when I'm integrating that middle guy, the x's will cancel out. We're going to have a 1/2, and it's going to be 1 over u du. It's going to be another natural log, but it's going to be natural log of our u. So putting all of that together, antiderivative of the first guy, natural log absolute value x. For the second guy, we're going to have that 1/2 that shows up from our u substitution. And then I get natural log absolute value of my u, which was x squared plus 4. And then this last guy is an inverse tangent. It was a 1 over x squared plus a squared is 1 over a, so that's 1 over 2. Inverse tangent of x over a, that's x over 2, plus c. And there's our answer. So technically, we don't need the absolute values on the second natural law because x squared plus 4 is always going to be positive. So we don't need the absolute value. All right, so that was case 3, what if you have a quadratic factor. But now you might be wondering, what if we have more than one quadratic factor, like the same quadratic factor but repeated? Well, that is going to be case 4. So we're going to write out case 4 and do one full example of case 4 all the way through. So case 4, your denominator has a repeated quadratic, irreducible quadratic factor. So if we have a factor that looks like ax squared plus bx plus c, and it happens r times, well, it's just the same as with the repeated linear ones, except you're going to have powers of the quadratic instead of powers of a linear. So we will have these following terms in the partial fraction expansion. It will look like a1x plus b1 over your ax squared plus bx plus c to the first power, and a2x plus b2 over your quadratic to the second power, and then to the third and fourth, and so on, until you get to arx plus br to that, or underneath that, you'll have your quadratic factor to the r power. So you have one term for each power of that quadratic factor. Very similar to the linear case. Only difference is instead of just having a number on the top, we're having a linear term on top, an ax plus b. So, for example, if we were going to just write out what the form of a partial fraction expansion looks like for this, x to the third plus x squared plus 1 over x times x minus 1 times x squared plus x plus 1 times x squared plus 1 to the third. Well, it's going to be kind of a mess, but take a look at it. We're not going to find all the constants, so don't freak out about that. We're just going to write out what the form would look like. We have linear, linear, quadratic, and quadratic that's repeated 3 times. So the partial fraction expansion of this, first linear term, I would have a over x. Then I have another linear one, so that's b over x minus 1. Now for the quadratic factor, x squared plus x plus 1, we need a cx plus d on top. And then for this last quadratic factor, I need first the x squared plus 1 to the first power with ex plus f. And now I need the x squared plus 1 to the second power. So that will have a gx plus h. And x squared plus 1 to the third power with an ix plus j. So just notice that we have one term for every factor, including every power of that repeated factor. So it would be kind of a mess finding all of these, but in theory, you could find the partial fraction expansion by multiplying both sides by the factor denominator and solving for a, b, c, d, e, f, g, h, I, and j, which luckily we're not going to do in this video. If you really want to, you can try it on your own. All right, let's do one example all the way through with a whole integral where we're going to have this last case involved somewhat. The last example for the video. Let's find the integral of 1 minus x plus 2x squared minus x to the third all over x times x squared plus 1 squared with respect to x. So we should first take a look and see if we need to do long division. Luckily, we do not. If I were to distribute everything on the bottom, I would actually have an x to the 5th power. So I have a larger power in the denominator than in the numerator. So no long division is needed. It's already factored for us. So we can just go ahead and set up the expansion. Notice that I have a linear factor x, and I have a quadratic factor x squared plus 1 that's repeated 2 times. So for the linear factor, I'm going to have a over x. And then for the quadratic factor, I need 2 terms. One of them is bx plus c over the quadratic factor. And the other one will be dx plus e over the quadratic factor squared. And now if I multiply both sides by the factor denominator, I get 1 minus x plus 2x squared minus x to the third equals a times x squared plus 1 squared plus a bx plus c times x and x squared plus 1 plus a dx plus e times just x. And I would suggest that we plug in x equals 0 and figure out what a is to start. So if I plug x equals 0 into this, the left side will become 1. The right side, I'm going to have my a times 0 squared plus 1 squared. And then this bx plus c term goes away because I have an x multiplied. And same with this last term, it's multiplied by 0. So I get 1 equals a times 1. So a is 1. And now let's plug that into our original to try to simplify this a little bit. I have 1 minus x plus 2x squared minus x to the third equals, if I plug in a equals 1 into this guy, we're going to have, let's see, that will be an x to the 4th plus 2x squared plus a 1. So I just distributed my x squared plus 1 squared. And then I have all of those guys as well. That's going to be a, keep distributing. I'm going to have x to the third plus x times the bx plus c. So I'm just going to write bx plus c times x to the third plus x. We still have to distribute all of that. And then I have a dx squared plus ex when I distribute that. So let's keep distributing. 1 minus x plus 2x squared minus x to the third equals x to the 4th plus 2x squared plus 1 plus bx to the 4th plus bx squared plus cx to the third plus cx plus a dx squared plus ex. Lots of fun, right? So from here, let's go ahead and move these first 3 guys to the other side because they don't have any b's, c's, d's, or e's to solve for. Well, actually, I'll leave the x to the 4th alone. No, I won't. I'll move the x to the 4th. Let's move all of that to the other side. It'd be much easier to look at. So if I move the 1 to the other side, that 1 cancels out. I'm just going to have a minus x Move 2x squared to the other side, and that goes away. I still have my minus x to the third, and now I have a minus x to the fourth as well. And on the right side, I have a bx to the fourth. That's that guy. I have a cx to the third. For my x squareds, I have a b and a d. So b plus d x squared. And for my x, I have c and e. So c plus e times x. All right, so now let's take a look at what we got. Comparing both sides of this equation, I can see that my coefficient of the x on the left side is -1. My coefficient of x on the right side is c plus e. My coefficient of x squared on the left is 0, and on the right, it's b plus d. Coefficient for x to the third on the left is -1, and on the right, it's c. Coefficient of x to the fourth on the left is -1, on the right, it's b. Notice we already got c and b just from doing that. B is -1 and c is -1. Well, then if I plug that information into the other equations, this tells me -1 equals my c, which is -1 plus e. So e is 0. And then this guy, b plus d equals 0. Well, b is -1. So 0 equals -1 plus d, tells me d is 1. So I had a was equal to 1, we had that earlier. B is -1, c is -1, d is 1, and e is 0. And now we're ready to write out the expansion so that we can integrate. So we have our original integral, 1 minus x plus 2x squared minus x to the third over x times x squared plus 1 squared dx. And we're going to write that using its partial fraction expansion. We had our a over x plus my bx plus c. B was -1. My c was -1 over x squared plus 1. And then plus my dx plus e. D was 1. E was 0 over my x squared plus 1 squared. So there's my partial fraction expansion. And just like we did on the other problem, I'm going to split this middle guy here into 2 fractions. So I'm going to have a 1 over x. I have a minus x over x squared plus 1, and a minus 1 over x squared plus 1. And then this guy is x over x squared plus 1 squared dx. And now let's just take a look at how we integrate this. First guy is a natural log. Second guy is going to be a u substitution, and it's going to give you a natural log eventually. This one is an inverse tangent, and this one's just a u sub. So let's go ahead and just write out a little bit of information on how we're going to do this problem. If you need to show the work for each individual integral, that's perfectly fine. Once you do a lot of these, you get used to them and might not need to show the explicit u substitutions anymore. So this guy here, our second term, is going to use u equals x squared plus 1. Du would be 2x dx. So du over 2x is dx. So you're going to end up with a 1 over 2 times a 1 over u, negative 1 over u, du. For this last guy, you would do u equals x squared plus 1, du is 2x dx, du over 2x is dx, and so that integral will end up looking like a 1/2 times a 1 over u squared du, which you would rewrite as a 1/2 u to the negative 2 du, and do that integral. So this first u substitution, you're still going to get a natural log. That other one, you're going to have to use a power rule. So all together, integral of 1 over x, we're going to get natural log absolute value x. The middle guy with the u sub, we're going to have a minus 1/2 natural log absolute value of u, and u is x squared plus 1. Middle guy here, that's an inverse tangent. So I have minus inverse tangent of x. The a's in that formula are all 1s. And then this last guy, I'm going to have my 1/2 u to the negative 1, so that would be a u in the denominator, x squared plus 1, and it's going to be negative from dividing by the new exponent, plus your c. And that is my nice, complicated answer for the problem. All right, so that is partial fractions. I personally think it's kind of fun. I'm sure you probably are not very happy right now, but the more examples you do, the better it will get. Now, your main clue that you need to use partial fractions, it looks like a rational function, polynomial over polynomial. And once you get through all of the algebra, the calculus ends up not being that bad. Pretty much all of the problems, once you get through the algebra, you're going to have natural logs, inverse tangents, and a couple u subs, but nothing too terrible for finishing up the final integral. If you have any questions, feel free to drop them below. If you're a current student, you can also email me or ask in office hours or class. And I'll see you guys next time.